Richard, you will do this in English. We will, you will have your slides ready. So welcome and please proceed.
Thank you very much, Anders, and thank you, William, for the introduction that you've given. We are talking about landfill mining approach for resource recovery from glass dumps into the circular economy. And as it has been said, this is a part of a thesis that was defended a few months ago in the beginning of May. So we have a problem here, and the problem that we are trying to find out is what kind of methods can we bring into the management of waste so that we can do this in a circular economy pattern. And so my name is Richard Mutafela, and I'll be talking about this. Thank you. So our study area is the Glasriket, or the Kingdom of Crystal, which is in the southeastern part of Sweden. And in this southeastern part of Sweden, it was known previously for glass production, a lot of crystal glass production. And so in our work, we focused on 4 different municipalities in the Kingdom of Crystal. And so in this Kingdom of Crystal, we have over 40 contaminated sites. And these are contaminated with different elements, for example, arsenic, cadmium, and lead. So this is more like a time bomb, if I may put it that way, because these materials, they affect the environment, groundwater, as well as health effects in this area. So we find that in this area, we have more than 1 million cubic meters of contaminated soil, as well as glass. And then almost like 500,000 cubic meters have been, of these contaminated materials have been found in only 22 sites. And of these, we have more than 3,000 tons of lead. So this is something that we need to work with. And this is something that has been more like the main problem. But then I need to ask a question to say, how did we get here? How did we get to this situation? So we take a look at crystal glass. Crystal glass, it's very beautiful as we know it, but in crystal glass, it's a lot of metal oxides that are used to give the glass different qualities that it has. So a lot of lead was used, a lot of arsenic, as well as antimony for different purposes. For example, on this other photo, you can see that if you needed to come up with different colors of glass, you needed different metal oxides. I've given an example of uranium and cadmium. These were used to come up with these highlighted colors. So currently, this is the way the Kingdom of Crystal looks. Unfortunately, it's a lot of dumps, like I said, more than 40 of them. And on the left part of the screen, you can even see the authorities have put a warning or a caution that we don't have to enter these areas because they're highly contaminated. And then on the right-hand side, you can see that in some of the sites, you end up finding these materials displayed even on the surface of the dump. So the background of our study is that we have these contaminated materials and contaminated dumps, which are taken to engineered landfills. They are more like excavated. But then we want to bring in circularity, and so we come up with a landfill mining approach. So whereby we excavate these dump materials, but we don't take them to engineered landfills. We do decontamination and recirculation of the dump materials. For example, we can take out the soil, and then we do phytoremediation like William talked about. We can also use the land later on. For example, what is on your right-hand part of the screen, that is a site that is in one of the Glasriket areas. We can turn them into parks instead. And at the same time, we are using plants through phytoremediation to take up all these masses. And at the same time, from the lead and the glass cullet that we get as we do the landfill mining approach, we can use these in circular products. For example, we could use the lead in different areas, such as we can use it in ammunition industry, which even though it's such a bad example, but we could also use it for radiation protection. Then the glass skillet, we could use it to come up with new glass artifacts. So when you look at this, our background, it looks more like some good model kind of, whereby we can get these materials and then turn them into circular products. And as you can see, we might end up with a few materials that are contaminated that we then take back to the engineered landfills. But then, how do we do this? There are a lot of uncertainties about this. So in our thesis as our framework, we have resource recovery potential as the main goal. So how we divided our thesis is, we have three different sections. The first one is the waste characterization. And in this waste characterization, basically, we're trying to know the characteristics of the waste, which is very important for our planning of remediation steps. And then we have dump site mapping. I'll explain in a later slide what these are. And we have metal extraction as well. So how these are connected is that when we do waste characterization, it gives us information, for example, about how do we sort our waste and what kind of materials and how polluted is this waste. And then once we have this information, ultimately, we want to have these materials and put them into the temporary storage, because as at now, we are still developing the metal extraction processes. But in the meantime, the materials are being excavated and dumped. So in this waste characterization, we can find information on how we can safely store our materials towards metal extraction and finally resource recovery. So in the first instance, I'll talk about waste characterization. I'll not take much time on this because it's not the main part of the presentation for today. So in the waste characterization, yes, we did different works. The first thing that we did in 11 different sites, we would go to a site with an excavator, we excavate the materials, and then we do hand sorting and sieving. In a laboratory, we needed to find out, for example, particle size distribution, and also do leaching tests to know what kind of contaminants would leach out. And also we went a step further to do radiation measurements, radioactivity measurements. Like I said in the beginning, they use partly uranium. So we are saying that before we put these materials into a circular economy, how bad are they? So then we find that actually we are able to see with these radioactivity measurements whether our materials are bad or they are okay. So for the waste characterization, I will not give you too many details, but then for the waste characterization, what we have is we have very heterogeneous material, and that is the way it looks. So what we are trying to find out is, when we look at these materials, is it possible that we can get materials that are cleaner than what we are seeing on the screen? Because when we go to metal extraction, this kind of material is not very good quality for the metal extraction process, which has got a quality requirement. So how do we then come up with a solution to this so that we present very good quality materials to the glass melting process? Okay, and that takes us to the main part of our presentation for today, which is dump geophysical mapping. So what we are thinking of, our hypothesis is that there are different sections in the dump site where we could find glass, like in hotspots or in a pure stance, if you will. And these positions, like when we do excavate in a conventional way, it's more like the glass mixes with other materials. Hence, we see the previous picture, what we saw, a very complex mix of materials that we can't work with. Instead, what we do is the following. We use electrical resistivity tomography, which is a geophysical measurement tool. So what we do is, when we go to our site, on the top part of the slide, you can see we have different mechanism. We've put up different equipment that we are using, we need a current transmitter, and then we need to transmit through very long cables on a site. And then these cables are connected to electrodes which go in the ground. So basically what we are doing is we are introducing current into the ground, and then we are measuring resistivity of all the materials, because naturally each material has got its own resistivity range. And so on the bottom left, we are seeing the principle, the way it works. So we are measuring potential difference between each pair of electrodes. And on the right, what we see is actually the way it is laid out in the field. So what we did is we thought that this could work in a glass site for us to identify the glass hotspots before we excavate. So what we started with was to go to a site that is more like just a heap of glass. We tried it on that site, and then later on we used this site more like a control before we could go to the next part. So this is the way we did. On the left parts, we have the cables running on the open dump site. And then on the right hand, we have the cables running on a dump that is closed, where we want to find the glass hotspots. What did we get then? So we get 2D resistivity profiles. And in these 2D resistivity profiles, you can see we had like a 40-meter long cable. And in this, we can clearly see the very high resistive material, which is definitely the glass bar, because glass is highly resistive material. And on the bottom there, we can see a resistivity scale. We already knew the resistivity from literature, the resistivity of glass, but we needed to try it on our glass to have a feeling of what it is. And then we went to the next site now. In this next site, this is the covered site, and this is what we see. You can see that we've got a very clear dump base. And then when we have this clear dump base, we start identifying the different materials. And according to the resistivity, we can easily see where the glass hotspots are, but we can also see the other materials. In this particular case, it aids us to plan what we can do for other recyclables apart from the glass that we have. So once we have gotten these 2D profiles, what we do is we incorporate these 2D profiles into some mapping softwares, such that when we give this information to people who will be digging, we are able to pinpoint the exact GPS locations of the glass hotspots. For example, you can even see that we've even given an estimation of this particular dump, where they can find where they should concentrate on digging for them to have the glass hotspots. When we go out, this is what we find. Once we have these results, we do digging of the materials, and we find that actually we were able to identify the glass hotspots. And this particular case, we found glass hotspots always greater than 87% glass content. Sometimes it would be as high as 99%. And also for the photos on the below there, it's just the other things that we're seeing, just to give you an indication of that. Actually, we're finding other materials like construction materials and all that kind of thing, but we can easily differentiate between the two. So now, once we have successfully gotten our glass, then we present to the metal extraction process. I should pause and say here that the next presenter is going to talk about metal extraction, but we thought that in this particular case, we should use a low energy process instead. So in this low energy process, what we decided to do is we crush the glass, and then after crushing the glass, we use extraction with nitric acid as well as chelating agents. So why are we doing this mechanical activation? Is to increase the surface area of the glass, as well as to bring down the particle sizes to increase the efficiency of our extraction process. So what I was saying is, in the beginning, we have a very big part of glass size, and then we crush it, and finally we mill it to very, very fine powder in nanometers. And then we can see that we are increasing the surface area, like I said, and then we are also increasing the leaching potential. Then what we did then was to used this very fine powder, and then we did extraction experiments between half an hour to 12 hours with a concentration of about half mole to 3 mole, and the temperature range of 25 degrees to 95 degrees Celsius. So what we found was that actually we could extract lead in this particular case. The highest potential was about 78% at 95 degrees Celsius. So in the graph on the left, we are showing the concentration effect. And in this concentration effect, what we are saying is that the concentration doesn't matter. 0.5 molar and 3 molar, the extraction is the same, which is a very good advantage in that we can use very low concentration of acid or chelating agent to come up to the same extraction efficiency. And then with the temperature effect, we are seeing that we saw that temperature has got the highest effect. In terms of time didn't matter much after 2 hours of extraction. So basically, these are the processes in a nutshell that we did. So once we had done all this, we came to the following conclusions that actually the waste was very hazardous, but like I said, there were no radiological risks of recycling it. And then we could see that with dump site mapping, we can pinpoint the location, the actual location of the glass hotspots. And we can also manage with metal extraction at a very lower temperature, but in relatively lower temperature. And then we are able to increase this efficiency with some parameters that we've come up with. And we saw that actually this landfill mining approach is very applicable to the area of glass dumps, such that we could use it even in other areas to come up with a problem, with a solution, for this problem that we have in this region. So for the future research, what we saw is that, especially for the dump site mapping, we found out that each geophysical method has got its own advantage and disadvantage. So if we use different ones together, they complement each other. So basically, this has been our work. Thank you for your attention.
Thank you, Richard. Could you have been working with this for several years now. What would you say is your key takeaway? And please make it short if you can. Yes,
the key takeaway from this is that these environmental problems that we have with the pollutants and all that, when we try to solve them in isolation, we may not come up to the solution that we need. We need to have different fields come together, and then we get an integrated solution. We don't need to have an isolated approach to environmental problems.
Okay, thank you. Då ska vi gå vidare till